Hello and welcome to Aakash BYJU's JEE YouTube channel. My name is Atiullah and we are live once again with JEE Mission 2022. So before we begin, just let me know if you can hear me properly and you can see me clearly. Give me a yes, give me a thumbs up so that we can quickly get started with this very important session. Alright, people joining in. Hi Ankit, how are you? Abhijit, TBS, Ritesh, hi guys. How are you? How are you doing? What's going on? Alright, quickly let me know if you can see me and hear me properly, and we are going to get started very soon. Alright guys, all good, all set? Alright, hi Shivam, thank you for letting me know. Hi TBS. Alright, so you can see me properly and hear me clearly, so we are good to go. So, the topic for today is rotational motion. Okay, very feared topic. बहुत डर लगता है इस टॉपिक से. Okay, everyone says it's a very difficult topic. कुछ समझ में नहीं आता है, बहुत difficult question आते हैं. Okay, partly true. I would not disagree. Partly all of it is true. It is, you can say it is a challenging topic because it's like a Bollywood masala movie. Okay, it has everything. It has action, romance, drama, everything. So if you have to study rotational motion, you have to know all the preceding chapters very well. So you have to know kinematics, you have to know laws of motion, friction, work, power and energy, center of mass, collision. You have to be thorough with all these chapters. And the reason most people are not able to follow rotational motion is because the preceding chapters are not done very well. But don't be afraid. Number one thing, pay attention to the basics. Okay, the basics should be clear. And number two, don't worry too much about rotational motion. There are so many other chapters which are easier, which are more scoring. So don't worry about rotational motion. Don't go too deep into rotational motion. If you're finding it very difficult, it's all right. Just get done with the basics and you should be good to go. Okay, so don't pay too much attention or don't destroy your life just focusing on one chapter. Okay, there are many chapters and much more scoring as well. Okay, but having said that, it is important to know at least the basics. So our idea here is, number one, to revise the basics, and number two, the idea is to take the fear of rotational motion away from you. So we are going to solve previous year papers and you will see that the questions are not really difficult. They are very simple and it's mostly about knowing your basics right. That's it. Okay, so we are going to get started with this session. So if you're ready, you know the drill. You take out your notebook and pen and we're going to solve all these things together. We're going to together beat all the questions to death. Okay, so if you're ready, let's get started, and here is the first question right at you. Alright, so what is the question? A stone of mass m is tied to the end of a string, is whirled around in a circle or a horizontal frictionless table. The length of the string is reduced gradually, keeping the angular momentum of the stone about the center of the circle constant. That is a key statement over there. Then the tension in the string is given by T is equal to A into R to the power n, where A is a constant and R is the radius, which is the instantaneous radius because the radius is changing. The value of n is equal to. Alright, so that is the question. Now first I'm going to ask you, what is the concept? Or let me keep the question right over here if you want to read it again. But the first thing I'm going to ask you is, what is the concept involved and how are we going to proceed with this question? First I want to know from you and then we will start to solve this question. Okay, so quickly let me know, what do you think? What do you think? How should we begin to think about this question? There's a pop-up. There's a pop-up. Any desk. Yes, guys. Captain Jack Sparrow, please explain the question. All right, Jack Sparrow, Captain, I'm going to explain this question again. So what you have is, you have this mass m over here. It is kept on a frictionless horizontal table, okay, and it is being rotated in a horizontal circle. How is it being rotated in a horizontal circle? Because someone is pulling on this thread, okay, someone is pulling on this thread very slowly, very gently. The person is pulling on this thread. So what is going to happen? The radius of the circle is going to reduce, Okay, as the thread is being pulled down, the radius of the circle is going to reduce. Okay, now very important thing given in the question is that the angular momentum of the stone about the center of the circle is constant. Okay, so it is changed, the radius is changed in a manner such that the angular momentum of the stone about this point over here is constant. Okay, and the tension in the string is given by A into r to the power n, where A is a constant and r is the instantaneous radius of the circle. Why instantaneous? Because the radius of the circle is changing. Okay, we have to find what is the value of n. Right, so I think the question is clear. So guys, I want to know from you, what is it that we are going to do in this question? Okay, angular momentum conservation. Okay, Siddharth has got that, and that's partly true. Absolutely, there is angular momentum conservation because obviously it is given in the question that the angular momentum is going to be conserved. Okay, what else? What else do we have to do in this question? So apart from angular momentum conservation, which is absolutely right and it is given in the question, what else do we need to do? Okay, the hint is right there. It is circular motion. So obviously we have to use the equation for circular motion. Alright, so let's see how to solve this question. Okay, so we have this mass over here. Now see, what I have done is I'm giving you a top down view. Okay, I'm giving you a bird's eye view. Okay, so I'm looking at the table from the top. Okay, the table is horizontal, but I'm looking from the top. This is this view. Okay, from the top. So that this is going to appear to me like this. Okay, now it is rotating in a circle. Now let's see what are the forces involved. The forces would be mg going into the plane of the screen. Okay, mg is going to be like this, downwards, which means in this figure it is going to go into the plane of the screen, and the normal from the table is going to come out of the plane of the screen. Okay, and there is going to be a tension in this string. Is that correct? Okay, so n is going to cancel out mg, hence there is going to be no torque because of n and mg about this point, and tension is passing through this point. So what will be the torque of tension? The torque of tension through this center is going to be 0, which means there is no net torque on this object, hence the angular momentum is going to be conserved. Pay attention guys, that even if in the question it was not given that the angular momentum is conserved, looking at the dynamics of the problem we could have figured that out ourselves. Okay, so we can say that, let's say this is moving with a speed v, and at this instant the radius is r. Okay, it is moving with a speed v and the radius is r. What is the first equation we can write? Okay, what is the centripetal force? What is the net force towards the center? mg is going into the plane of the screen, n is coming out of the plane of the screen, so mg and n have no contribution to the centripetal force. So the net force towards the center is tension, and tension is going to be equal to mv square upon r. This is the centripetal force. Is that right guys? Tension is equal to mv square upon r, correct? And that is given to us as a into r to the power n. Okay, so in the end, when we calculate tension, we are going to compare it with a into r to the power n. That is number one. What is the second thing? How do we conserve angular momentum? Can you tell me what will be the angular momentum of this particle about the center? Absolutely, Yash, you're absolutely right, and that's exactly what we have written. Tension is going to be mv squared by r, but I want to know from you, what is the angular momentum of this particle about the center? Can you figure that out? Sachin, if you are answering for angular momentum, then no, 0 is not going to be the answer. The angular momentum is going to be conserved. Alright. Yes, Yash, you are absolutely right. The angular momentum is going to be mvr. Absolutely. So let's look at this. Let's look at this. So it has a mass m and it has a speed v. And what is the perpendicular distance from the center? Okay, what is the perpendicular distance from the center? The perpendicular distance from the center is r. Is that right? Okay, so what are we going to say? That the angular momentum is going to be mvr. Is that right? Okay, so Urmila is asking, kaise conserved, sir? Okay, so if you are asking about angular momentum, so see, one, it is given in the question that the angular momentum is conserved. Second, mg is acting downwards, normal is acting upwards. Okay, so n is going to be equal to mg. So the net force because of n and mg is going to be equal to 0. Okay, so the torque because of n and mg is going to cancel each other out. Okay, and the torque of tension is going to be 0 because tension is passing through the center. Is that right? In that case, the torque of tension is going to be 0. So what is the net torque on the particle about the center? It is 0. So the angular momentum is going to be conserved about the center. Okay. And what is the value of angular momentum? The angular momentum will have a value of mvr. Is that right? Okay. So now we have to use this equation, and we have to use this equation to somehow eliminate v. Okay. So let's try to do that. Let's try to eliminate v. So what I'm going to do is I'm going to write t as, okay, so in this equation we have a term of VR. Is that right? So we are going to make use of that. So I'm going to write tension as m into VR square divided by r cube. Can I write that? Just check and let me know. Can I write tension as m into VR square divided by r cube? Just check and let me know if I can write that or not. Urmila, you are very welcome. Okay, so Sur is asking, sir, please tell whether the concept of instantaneous axis of rotation helps in combined translation and rotational motion or reduces calculation. It certainly reduces calculation, but it's not necessary that in every question it is going to reduce calculation. Okay, and I'm going to show you in this session where it can reduce calculation. Don't worry about that. I'm going to handle that in this session. Okay, so we have tension like this. So from here, can we write VR is going to be L by M? Okay, and we see VR over here, so we can simply substitute, right? So this is going to become T is equal to VR. The value of VR is going to be L by M and the square of that, and we have 1 upon R cube. Is that correct? So what do we get? We get L square upon M and R to the power minus 3. Okay, so what is the final expression we have got? The final expression we have got is tension is equal to L square by M into R to the power minus 3. Now you can see that L square upon M is going to be a constant. Angular momentum is constant and mass is obviously going to be constant. So what do we have? Now can we compare this with A to the power A into R to the power N? Okay, so now it becomes very obvious that your answer is going to be N is equal to minus 3. Is that correct? Is that right, guys? So what is going to be the correct option? The correct option is going to be option D, minus 3. Alright, so is the solution clear? Is the concept clear? Two concepts we have used over here. Number one, the conservation of angular momentum, and number two, because it is circular motion, we have used the equation for circular motion. The net force towards the center is equal to mv square upon r. That's it. Yes, Yash, the answer is minus 3. Alright, guys. So very quickly, let me know what do you think is the difficulty level for this problem. Quickly let me know. सचिन क्या हो गया? ओहो सर क्या हो गया? Silly mistake कर दिया? Alright, so 3 out of 5. I think that's fair. 3 out of 5 to this question is alright, but it would have been a better question if it was not mentioned in the question that the angular momentum is going to be conserved. That would have been a little better question. Alright, Yash, thank you. It's absolutely clear. So let's move to the next question. Are you guys ready? So here comes the next question. Alright, another very interesting question. 7 identical circular plane discs, each of them has mass m and radius r, are welded symmetrically as shown. Okay, so there are 7 discs, each has mass m, radius r, and they have been welded to form a shape like this. The moment of inertia of the arrangement about the axis normal to the plane and passing through the point P. So we want the moment of inertia of this system through point P. Where is point P? Here is point P. Can you see? Here is point P. But the axis is going into the plane of the screen. It is perpendicular to the plane. It is perpendicular to the plane and going into the plane of the screen. Okay, so something like this. Okay, it is going into the plane of the screen. So this is the axis about which we have to calculate the moment of inertia. Is that correct? Is the question clear? Any confusion in the question? If yes, let me know. I'm going to resolve that. And if the question is clear, then you need to tell me what is the concept we are going to apply over here and how do we proceed with this question. Okay, doesn't look like a very straightforward question. It's not formula application. So, how do we start? How do we start with this question? Alright Siddharth, yes, the concept obviously is moment of inertia, but moment of inertia has so many different concepts within it. So what exact concept, and I can give you a hint, what theorem can we use to solve this question? Okay, and yes, Captain Jack Sparrow is absolutely right, we can use parallel axis theorem. Okay, let's see. What does the parallel axis theorem tell us? The parallel axis theorem tells us that the moment of inertia about an axis is going to be equal to ICOM, the moment of inertia about the center of mass, plus md square. Okay, so if this is the body, and we have two axes which are parallel, but the condition is one axis has to pass through the center of mass. It has to pass through the center of mass, otherwise we cannot apply it. Okay, so one axis has to pass through the center of mass. Then if we have to calculate the moment of inertia about the other axis, which is parallel, and the distance between the two parallel axes is d, then the moment of inertia about that axis is going to be ICOM, the moment of inertia about the center of mass, plus md square. Is that correct? Okay, so that is the parallel axis theorem. But now my question to you is, how do you apply parallel axis theorem in this question? That's what I want to know from you. Okay, so quickly let me know, how can we apply parallel axis theorem, which is absolutely right, which we have to apply in this question, but how do we apply that in this particular question? It's not a very straightforward formula application, as you can see. Right guys, what do you think is going to be the process through which you are going to apply parallel axis theorem? Okay, ये तो पता चल गया parallel axis theorem लगाना है, but कैसे? किस डिस्क के लिए? So there are 7 disks over here. So we have to find the moment of the moment of inertia for the entire system. So how do we go about it? First, I want to know from you. Finding the center of mass, okay, that looks like a smart answer, but finding center of mass is very straightforward. Captain, can you tell me where is the center of mass of the system? Just by using symmetry, just by looking at it, you can tell where is the center of mass of the system. Correct, it would be right over here. This would be point O. The center of mass of the system is going to be point O. Okay, so let me tell you. Okay, so one way of solving this question is that you know the moment of inertia. Let's take the central disk. Okay, let's take the central disk. You know the moment of inertia about O. Is that right? So for a disk, what is it? It is mr square by 2. So you know the moment of inertia about point O. Now we know that this distance is going to be how much? This distance is going to be 3r. So we know that distance. So we can find the moment of inertia of the central disk about point P. Not a problem at all. Perfect. But then we have this disk over here. So we'll have to find out what is this distance. Do you agree? This is going to be 2r. And then we'll have to find out what is this distance to find the moment of inertia for this disk, which we don't know, but we'll have to calculate. Okay. Then we'll have to calculate the moment of the distance between these 2 points. Right. So there are a lot of distances that we will have to calculate. Do you agree? There's a lot of distances and there's a lot of geometry that we'll have to use over here. Okay, so probably we have a better solution. Okay, and this is my suggestion for solution. Let me know if it is better or not. Okay, so this is my suggestion. So we know what is the moment of inertia of the central disk. Fine. Okay, now what we can do is we can find the moment of inertia of all these disks about the center. Okay, we can find the moment of inertia of all these disks about O. Can we do that? Very simple. We know the moment of inertia about this point. Do we know that or not? Okay, that's mr square by 2. And what is its distance from this point? That distance is 2r. Is that correct? And the same situation is there for all the disks. So if you calculate the moment of inertia of one disk about O, the moment of inertia of the rest 5 disks which are on the periphery is going to be exactly the same. Okay, so what does it tell me? It tells me that I can find the moment of inertia of the entire system about O. And what is O? O is the center of mass of the entire system. And once we know the moment of inertia of the entire system about point O, then we can use parallel access theorem directly to find the moment of inertia about point P. Is that correct? So that is my action plan to solve this question. Do you agree? Do you think this is a better method, or is it easier to find out the distances for all the disks separately? Alright, so let's see. Okay, let me rub this off. And then let's start solving this question. Okay, first things first. What is the moment of inertia of the first disk? Let me number it. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. So what is the moment of inertia of disk 1 about point O? The moment of inertia of disk 1 about point O is going to be mr square by 2. Agreed? Agreed. Okay. Can I find the moment of inertia of disk 2 about its center? Okay, let's say we call this O prime. We call the center of disk 2 O prime. So that is going to be how much? That is going to be mr square by 2. Okay. But now I want to find out the moment of inertia of disk 2 about O. What is that going to be? That is going to be ICOM plus MD square. Do you agree? Now I'm applying the parallel access theorem. So what is this going to become? What is this moment of inertia about the center of mass for disk 2? We have just calculated that, haven't we? We have just calculated that. So that is going to be mr square by 2 plus what is the distance between O and O prime? That is going to give me D. What is that distance? Now that is very easy to see that that distance is going to be 2r. Okay, twice of the radius. So this is going to become m into 2r square. Is that correct? So what is this going to give me? This is going to give me mr square by 2 plus 4 mr square. So this is going to give me 9 mr square by 2. So this is the moment of inertia of disk 2 about point O. Now the moment of inertia of disk 3, disk 4, disk 5, the moment of inertia of disk 3, disk 4, disk 5, disk 6, disk 7, all of them are going to be the same. Do you agree? Okay, all are going to be the same. Okay, so now we can say that the moment of inertia of the system, okay, the moment of inertia of the system, the entire system about point O is going to be the moment of inertia of the central disk. Okay, the moment of inertia of the central disk, how much is that? mr square by 2 plus the moment of inertia for the other disks. How much did we calculate? We calculated that as 9 mr square by 2. Okay, so this is going to be how much? This is going to be 9 by 2 mr square. But this is for one disk. How many such disks do we have? We have 1, 2, 3, 4, 5, 6. We have 6 such disks. So what should I do? I should simply multiply it by 6. Is that correct? Because for all these 6 disks, the moment of inertia is going to be same about point O. Okay, so this is going to give me the moment of inertia of the system about O. And how much is that going to be? That is going to be mr square by 2 plus, so this is going to become 27 mr square, and this is going to give me 54 and 155 upon 2 mr square. Is that right? But is the job done? Not really. We don't have to find the moment of inertia of the system about O. We have to find the moment of inertia of the system about point P. Okay, about the axis passing through P. So the good thing is that we have already calculated the moment of inertia of the center of the system about the center of mass. Is that right? For this entire system, the center of mass is at O. So now we can directly apply the parallel access theorem. Now what is this distance? What is the distance between the parallel axis? The distance between the parallel axis is 3r. Do you agree? So now I'm going to apply and find out, I'm going to apply the parallel axis theorem. I'm going to find out the moment of inertia of the system about point P. So that is going to be the moment of inertia of the system about point O, which is the center of mass, plus md square. And how many masses are going to be there? So what is going to be the total mass of the system? The total mass of the system is going to be 7m. Okay, so here I have to use 7m, that is the total mass of the system, into d square. Is that right? So now it's very easy to see. This is going to become 55 upon 2 mr square plus 7m into d square. D square is going to be 3r square, so that is going to be 9r square. Okay, so this becomes 55 upon 2 plus we have 7 into 9, which is 63 mr square, and that is going to become, so take the LCM, so this is going to become 126, and 126 and 55 is going to give me 181 divided by 2 mr square, and that is going to be my answer. Is that correct? Alright, so I see a lot of different answers over here, but unfortunately none of that is matching. So guys, check your solution where you went wrong, because the final answer is going to be 181 upon 2 mr square. Is that right? Is the concept absolutely clear? Alright, not a straightforward question, but we can find a good solution if we know the concept very well. Guys, can you check where did you go wrong? Because I'm getting this answer as 181 by 2 mr square. Alright, Captain Jack Sparrow is saying, I love the way of teaching, your way of teaching, sir, because you teach from first principles. Thank you so much, Captain Jack Sparrow. And yes, I think that's the best way to study physics. Okay, there is no other way. We have to learn everything from first principles. Okay, that's where our concepts are built. Perfect. So this is the answer. Guys, do you have any problem in the solution? Yes, Somnath, you have got that absolutely right. That is going to be 181 upon 2 mr square. Okay, so what is going to be the correct option? The correct option is going to be option D. Alright. Now quickly let me know what do you think is the difficulty level for this question. Alright, I know it's not a very straightforward question, but not very difficult also. Okay, it's just parallel axis theorem we have to apply. So what do you think? Quickly let me know what do you think is the difficulty level for this question, and then we'll quickly go to other questions. There are a lot of questions we have to solve today, a lot of different concepts. $3.54. All right. So I agree. It will rise somewhere between 3 to 4. Not very straightforward, but yeah, it was a bit calculation intense as well. Okay, but I would not say it is difficult. If you are comfortable with applying parallel axis theorem, should not be that difficult. Okay, perfect. So now let's go to the next question. Here is the next question in front of your screen. Okay, so what do we have here? We have a cylinder of mass m resting on a rough horizontal rug that is pulled out from under it with acceleration a perpendicular to the axis of the cylinder. What is the friction at point P? It is assumed that the cylinder does not slip. Okay, all of us has done that. So there is a cylinder which is kept on a rug and we are pulling the rug. Okay, this is the rug over here. Okay, you can think of it as a platform, you can think of it as a rug. So the rug is being pulled out with an acceleration a, and the cylinder is kept on top. So the cylinder is also going to move along with it, and the key information provided here is that the cylinder does not slip. The cylinder does not slip. That is the key information provided here. Okay, so what is this? This is rolling without slipping. Can you see that? This is rolling without slipping. So what we have to find out is what is the friction acting at point P. Okay, we have to find out what is the friction acting at point P. Is the question clear, guys? And if the question is clear, quickly let me know how do you think we should proceed with this question. Okay, read the question again if you want, and then we are going to go to discuss how should we solve it. Alright guys, is the question clear? Hi Amrit, good to see you. How are you doing? Alright. Now first I want you to think, how is the cylinder going to move? Okay? How is the cylinder going to move? And when I say move, how the cylinder is going to translate and how the cylinder is going to rotate. I want both the answers. Okay? So what I'm going to do is, I'm going to assume that the center of the cylinder moves ahead with an acceleration a prime. Okay? I'm going to assume. Now, by your experience, you can say that the cylinder can come forward or the cylinder can go back as well. Okay? Both the possibilities are there. Either the cylinder can come along with the platform or the rug, it can come in the same direction, or the cylinder can go in the opposite direction as well. Okay? I don't know that, but I'm going to assume something. There's no problem with assumption. So I'm taking a prime to the left. If you wish, you can take a prime to the right, but be careful when we are using the constraint equation. Okay? So I'm assuming a prime towards the left. Perfect. Okay. How is the cylinder going to roll? What is going to be the direction of angular acceleration of the cylinder? Now think about it. You're pulling the rug like this. So the cylinder obviously is going to rotate in what direction? It is going to rotate in this direction. The way I'm seeing it, it is going to rotate in the clockwise direction. Is that correct? So I'm saying that the angular acceleration is going to be alpha. Okay, Captain is asking, is there any friction in rolling? Because only one point touches the ground. Yes, absolutely. There has to be friction, Captain. Two reasons. One, in the question it is given that you have to find the friction. So obviously there is going to be friction. And the second thing is, how else is this cylinder going to move? If there is no friction, what is the force which is going to make the cylinder move? So there has to be friction if the cylinder is moving. There is no other force which can do that. Mg is going to act like this vertically, normal force is going to act like this. They cannot contribute to its horizontal acceleration. Is that correct? Okay, so obviously there has to be friction. Alright, now is this clear that we have assumed the acceleration of the center A prime and we have assumed the angular acceleration of the disc or the cylinder alpha in the clockwise direction. Is that right? Any problem? Perfect. Now what I want from you is, can you tell me the relationship, and this is the most important part of the question. Can you tell me the relationship between A prime, A and alpha? This is the critical relationship that we need. If we are able to figure this out, then rest of it is just applying force and torque equation. Nothing great about that. But can you figure out what is the relationship between A prime, A and alpha? Okay, I'm going to wait for your answer. And the key to solving this is that this point P does not slip with respect to the rug. Okay, this point P, which is in contact with the rug, does not slip with respect to the rug. Okay, that is the key information provided in the question. How do we use that to find the relationship between A prime, A and alpha? If we can do this, then this question is going to be not difficult at all. So we have to make use of the fact that this is rolling without slipping. Point P does not slip with respect to the rug. What does it mean? If that is the case, then what does it mean? And how can we find out the relationship between A prime, A and alpha using that? Soumyadeep is saying, sir, first one came from equilibrium and torque equation. So equilibrium and torque equation we can apply, Soumyadeep. Obviously we are going to apply that, but there's a more critical thing that we have to solve first. We have to find the relationship between A prime, A and alpha. Okay, so we don't need torque and force equation to find that relationship. That relationship is going to come from constraint. That relationship is going to come, not constraint, but that relationship is going to come from the fact that this is rolling without slipping. Okay, so can we use that? Okay, so I'm going to give you a hint. When ground is stationary, okay, when ground is stationary, and if this object is in pure rolling, okay, when it is doing pure rolling, and it has an angular acceleration alpha and a linear acceleration a, and the radius of this object is r, then what is the relationship between a and alpha? Do you know this? This is very straightforward. So this ground is at rest. This ground is at rest. In this case, if this object is doing pure rolling, then what is the relationship between a and alpha? A is equal to alpha r. Absolutely, A is equal to alpha r. Okay, how do we do that? How do we do that? So what do? We say that the acceleration of this point, okay, which point? Let's call it Q. The acceleration of this point Q is going to be equal to the acceleration of this point over here. Because they are not slipping with respect to each other, then the acceleration of both the points have to be equal. Okay, so if this point is stationary, the point on the ground, it is stationary, it is not moving, the ground is not moving. So the acceleration of this point Q has to be 0. And how do we figure that out? We say that if it has an angular acceleration of alpha, then the acceleration of this point with respect to the center is going to be alpha r in this direction, and the acceleration of this center is going to be a in this direction, and net it has to be 0, which means a and alpha r have to cancel each other. Is that correct? This is how we find that relationship. Do you agree? So many times what we do is we simply remember a is equal to alpha r, but we forget how did we get that. What was the underlying principle behind a is equal to alpha r? We forget that. Okay, and that's why I want to revise that for you. This is how we find a is equal to alpha r. I'm sorry, this is a. This is how we find a is equal to alpha r. Is that correct? Okay, now we can apply the same thing over here. Now we are going to apply the same thing over here. Now the only point is that this rug has an acceleration of a. So the point on the rug does not have 0 acceleration. It has an acceleration a. So the point in contact should also have the same acceleration. Okay, so let's take this disk. So what is the acceleration with respect to the center? The acceleration with respect to the center is going to be alpha into r. Do you agree? The acceleration with respect to the center is going to be alpha into r plus the acceleration of the center. What is the acceleration of the center? The acceleration of the center is in this direction itself. So this is the acceleration of the center. So what is the total acceleration? The total acceleration, both of them are going to be in the same direction. So a prime plus alpha r. Is that right? And this is the acceleration of point P. And what is going to be the acceleration of point P? It is going to be equal to a, the acceleration of the rug, because the rug and that point of contact should have the same acceleration because they are not slipping with respect to each other. And that is how we find the relationship a is equal to a prime plus alpha r. Is that right? A is equal to a prime plus alpha r. Is this relationship between a prime, a and alpha absolutely clear? Okay, this is a very, very critical concept. It is going to come again and again and again, and it can be a source of error. If you simply remember a is equal to alpha r, a is equal to alpha r, it is not going to help. We have to understand why is a is equal to alpha r, and is a is equal to alpha r going to hold in all situations? It is certainly not holding over here. So what we have to remember is that if there is pure rolling, if the object is not slipping, if the point of contact is not slipping with respect to the surface, then the acceleration of the surface and acceleration of the point of contact have to be equal. That is the concept. Is that correct? Perfect. So we have found this relationship a prime. We have found this relationship a is equal to a prime plus alpha r. Okay, now it's very simple. Now we have to apply the force and torque equation. Very simple. Okay, so what will be the direction of friction on this object? Obviously, the only thing which can accelerate it in the forward direction is friction. Okay, so friction is going to act in the forward. Friction is going to act in the forward direction. Okay, so I can write that friction is the only horizontal force on this cylinder. So friction is going to be mass times the acceleration. Do you agree? That is my equation number 1. And then what is the torque of friction? The torque of mg and the torque of n is going to be 0 about the center. Do you agree? So what is the torque of friction? The torque of friction is going to be F into R, and that is going to be I into alpha. Moment of inertia of the cylinder about the center is mr square by 2 multiplied by alpha, and that is my equation number 2. Now from these two equations I have to find out what is the value of A. Is that correct? Now that's very easy. So this R and this R is gone, and then I can send this 2 to this side, and here I have MA alpha and here I have M alpha. Sorry, here I have MA prime and here I have MR alpha. Okay, so what I'm going to do is I'm going to add both the equations. So if I add both the equations, then this is going to become 3F and this is going to become M is taken common, and this is going to be A prime plus alpha R. Okay, and you can understand why I have done that, because A prime plus alpha R is equal to A. So from here we get 3F is equal to M into A, and from here we get F is equal to MA upon 3, and that is going to be my answer. Is that right? Okay, so once we had the relationship between A alpha and R, as said, the question becomes very simple. Okay, all you have to do is apply the force equation, apply the torque equation, and you are sorted. Okay, so the final answer, the friction is going to be MA by 3. And then what should be our correct option? Our correct option should be then option D. Okay, but look at the solution and let me know if this is absolutely clear. Is there any confusion? I'm happy to resolve that. Right guys, all good? All clear? Alright, so the correct option is going to be option D, MA by 3, and we are ready to go for the next question. Alright, so the next question right in front of you now. Okay, so we have a tennis ball, and you can treat the tennis ball as a hollow sphere, and it starts from O. Where is O? Here is O, and rolls down a hill. Again, I am going to circle this. Rolls down a hill. This is the most important word in the question. Okay, rolls down a hill at point A. Where is point A? Here is point A. The ball becomes airborne. Basically it means it becomes a projectile, leaving at an angle of 30 degrees with the horizontal. Okay, it becomes a projectile. It shoots out at an angle of 30 degrees from here. The ball strikes the ground at B. What is the value of distance AB? So basically what do we have to find out? We have to find out the range of this projectile. Now the moment of inertia about a diameter for the spherical shell is given as 2 by 3 mr square. Is that correct? So what do we have to find out? We have to find out the range of the projectile. And if we have to find the range of the projectile, what do we need? What is the range of the projectile? The range of the projectile is u square sine 2 theta by g. So basically in this question, all you have to find out is the velocity with which it gets projected. So you have to find the velocity of this circular, of this hollow sphere at point A. If you can do that, then this question is just formula application. Is that correct? But the important question is, how do we find the velocity of this tennis ball at point A? How can we do that? And I have thrown this question at you, and you are going to suggest what should we do. You are going to suggest what should we do. I'm going to wait for your answer. So there's no point giving the solution right away, okay? That's not going to really help you. So what I want to do is I want to really make you think. Unless you think, unless you try to do it yourself, then otherwise the session is not going to be really effective, okay? If you want it to be effective, you have to attempt, you have to struggle, you have to come up with your solution, okay? Team Up is saying we need to identify the friction. Alright, Team Up, I'm going to go a step further and ask you why. Why do we need to identify the friction? Is there going to be friction or not? Okay, so Soumyadeep is saying conservation of energy. Soumyadeep, I'm going to ask you one question again. Can we conserve energy? Can we conserve mechanical energy? Can we do that? Because the first thing we need to think is there going to be friction or not? Okay, is there going to be friction or not? That's the first question we need to answer. And if we understand that, okay, friction is there or friction is not there, then we can answer, can we conserve energy or can we not conserve energy? Okay, so the first question is there going to be friction or not? And the second question, the follow-up question would be, can we conserve mechanical energy or not? Alright, I'm not going to give you answers so easily. Okay, I'm going to make you work for it. Alright, Team Up, I'm going to show you the question once again, not a problem. I'm going to keep it here. People who want to read the question again, you're welcome to do that. Once you're clear with the question, then proceed with the solution. The first question is there friction or not? And the second question is, can we conserve mechanical energy or not? Interesting question, isn't it? Captain Jack Sparrow says friction hai. Agreed, Captain Jack Sparrow. I absolutely agree. Very good answer. Friction hai. Now, can you also explain friction? How can we say friction hai? कैसे बोल सकते हैं friction hai? Okay, and the answer is, it is rolling. Okay, this object is rolling. What they mean is it is in pure rolling motion. Okay, and unless there is friction, it cannot roll. If it were a frictionless surface, then it will slide down. It will not roll down. Is that correct? Okay, so if there is friction, only then it is going to roll. If there is no friction, it is simply going to slide down. Who is going to rotate it? Okay, absolutely. Lovely answer, Captain Jack Sparrow. Lovely answer. Absolutely. That is the reason why rolling is happening. Now the second follow-up question is that if friction is there, can we conserve mechanical energy? If friction is there, then can we conserve mechanical energy? How to answer that question? So one thing we have established is there is friction. For sure, there is friction. But then can we conserve mechanical energy? Captain Jack Sparrow says, no, we can't. Soumyadeep says, no, sir. Krishav says, no. Okay. Rebel says, yes. Okay, Rebel is living up to his name. People are saying, no, we can't. But Rebel is saying, yes. Alright, Rebel. Tell me, why do you think we can conserve mechanical energy? There is friction acting on the surface. There is friction acting on this tennis ball. Then why do you think we can conserve mechanical energy? Agreed, Captain. I get your point. It is not a conservative force. So basically, yes, it is not a conservative force. It is a dissipative force. So if it is acting, most times we cannot conserve mechanical energy. But rolling is a very special case. In rolling, what happens? Okay, so think about this. Let me show this to you. In rolling, so rolling is a very special case. What happens when something is rolling? The point of contact is stationary. When rolling is happening, the point of contact is stationary. where is the friction going to act? Okay, if it is rolling like this, where is the friction going to act? Friction is going to act like this. Okay, friction is going to act either in the forward direction or in backward direction. Irrelevant. The point is the friction is going to act at the point of contact. Do you agree? Now, what is work done? Work done only happens when there is a force and there is a displacement of the point of application of force. Now, this point of contact is stationary. So, is there displacement of the point of application of force? There is no displacement of the point of application of force. And the frictional force is acting, but the work done by the frictional force is zero, which means we can conserve mechanical energy here. Okay, so in case of pure rolling, even when friction is acting at the point of contact. The point of contact is going to be stationary because this is pure rolling, and hence the work done by friction is going to be zero. If the work done by friction is going to be zero, then it means we have the license to conserve mechanical energy. Is that right? Okay, so what do we have? We have work done by external force plus work done by non-conservative force. That is equal to the change in kinetic energy plus the change in potential energy. This is the work energy theorem. Okay. Alright, team up, I'm going to repeat this once again. So the work energy theorem tells me that the work done by external force plus the work done by the non-conservative force, which means the total work done by all the forces is equal to the change in kinetic energy plus the change in potential energy. Correct? Now there is no external force over here, or the work done by external force is zero. Normal force is not doing any work. Okay. Now friction, which is a non-conservative force, that is also not doing any work. Why is it not doing any work? Because the friction is going to act at the point of contact, and pure rolling means that the point of contact is going to be stationary. So when force is acting but the displacement of point of contact is zero, it means that the work is not being done by that force. And if the work is not being done by that force, which means this quantity is going to become zero, and delta K plus delta U, which is basically the total change in mechanical energy, that becomes zero, which means we can conserve mechanical energy. Is that correct? Are you comfortable with this concept? Okay, so we take conservation of mechanical energy for granted. We see the question, we get habituated to it, and without applying any brain, we simply go for it. And most of the time the thing is we get the right answer, but we forget what is the right concept, what is the concept, what is the underlying principle behind that. Okay, and that is my job today, to make you realize what is the underlying principle. Okay, you can find the solution in any book, you can find the solution anywhere, but the point is we have to understand at depth what is the actual concept. Is that correct? Alright, so this being said, now we are going to conserve mechanical energy and we are going to solve this question. Okay, so we see that it has fallen by a height of 1.8 meter. Do you agree? This entire distance is 2 meter and this distance is 0.2 meter. So it has fallen down by a distance of 1.8 meter, which means the loss in gravitational potential energy is going to be mg into 1.8. That is loss in gravitational potential energy, or for now we can just call it h. So the loss in gravitational potential energy is mgh, and it should be equal to the gain in kinetic energy. Okay. Now this is an object which is rotating plus translating. Okay, so this is combined rotation plus translation. So where should I draw? I should draw it over here. So let's say it has a speed v and it has an angular velocity omega. Okay, the center has a speed v and it has an angular velocity omega. Now in this case, how do we find the kinetic energy of the system? In this case, the kinetic energy of the system is given by the kinetic energy about the center of mass plus the kinetic energy of the center of mass. Okay, it is not simply going to be half mv square of or half I omega square. Remember, when there is translation plus rotation, then the kinetic energy is given as the kinetic energy of the kinetic energy about the center of mass plus the kinetic energy of the center of mass. So if we sit at the center, we'll see that it is rotating with an angular velocity omega. So I can write it as ICM, which is the moment of inertia about the center of mass, into omega square plus half into m multiplied by VCM square. So this is how we calculate the kinetic energy of an object which is both rotating and translating. Is that correct? Okay. So captain is saying, but sir, point of contact is displacing from O to A. No, the point of contact is not getting displaced. See, the point of contact changes. Now this is the point of contact, the friction is acting over here. But when this is going to go further, so let's say now this point over here is going to become the point of contact. The point of contact is not sliding. As soon as the point of contact gets displaced from that point, okay, as soon as this point of contact gets displaced from that point, it no longer remains the point of contact. Now the friction is not acting there. The friction now acts on the different point of contact. Okay, so in no case the point of contact is sliding. The point of contact, as soon as it moves, it doesn't remain the point of contact. Some other point becomes the point of contact. Okay, and that process is going to continue. So we'll never have a situation in which the point of contact is sliding. Alright, I hope that's clear. Okay, so what we have done is we have found out what is the moment of inertia, the kinetic energy of this object. So let's substitute now. So this becomes mgh is equal to half. What is the moment of inertia of, what is it? It is a hollow sphere, okay? What is the moment of the hollow, what is the moment of inertia of a hollow sphere about its diameter? This is 2 by 3 m r square. Okay, then we have omega square. Okay, now because this is in pure rolling, we can write v is equal to omega r as well. Okay, pure rolling hai. So we can write v is equal to omega r. We have discussed that, right? So for omega, I can substitute it by v square by r square. For omega square, I am substituting it by v square plus r square plus half m v square. Okay, so v is the speed of the center of mass. Is that correct? Okay, so from here r square and r square is gone. From here m and m is gone. So what do we get? We get gh is equal to this 2 and this 2 is gone. So we get 5 upon 6 v square. So from here we get v square is equal to 6 gh upon 5. Is that correct? Hi Vishal, good evening, very good evening. I'm good. How are you doing? Alright, hope you're following the sessions. Okay, so what we have done is we have found out what is the speed v, haven't we? We have found out what is the speed v, and we don't need to find v right here because we have found out v square and we are directly going to use v square. So what is the range? Now when it has become a projectile, the only force acting on it is the gravitational force. So we can simply treat it as a projectile. So if we can treat it as a projectile, then the range is going to become v square sine 2 theta upon g. What is the value of v square? It is 6 gh upon 5. Then sine 2 theta, theta is 30 degree. So this is going to be sine 60 degree and then divided by g. So this g and this g gone. So r comes out to be 6h by 5 into, what is sine 60 degree? It is root 3 by 2. Okay. So that is going to be the range. Now you can do the calculation. It's not very difficult. You can do the calculation and then you're going to get answer as around 1.87 meter if I remember this correctly. Yeah. So you're going to get the answer as option A, 1.87 meter. So I'm not going to do the calculation. It's a very simple calculation. You can do at your end. But what I want you to explain, what I wanted to explain here is two concepts. One, why are we sure that we can conserve mechanical energy even though friction is acting? So we have understood that. The second concept we wanted to understand was how to calculate the kinetic energy of a body which is both in translation and rotation. And this is how we do it. Is that clear? Perfect. Alright. So what I'm going to do is I'm going to rub this off and I'm going to address another question that somebody asked. So someone asked me that if we use instantaneous axis of rotation, then is that going to help us? If we use instantaneous axis of rotation, is that going to help us? Okay. Okay. Right. So let's try to understand that. So we have a cylinder, or we have a what is this, hollow sphere. Okay, we have a hollow sphere which is doing pure rolling. So when it is doing pure rolling, then it means that this point is stationary. The point of contact is stationary. Okay. Now if this point of contact is stationary, then what we can think of it is that this entire sphere is doing pure rotation about the instantaneous axis of rotation, about this point, about the point of contact. Think about it. Okay, so it is rolling, okay, but just think that for a moment that this point is stationary, and when this point is stationary, this entire thing is going to be in pure rotation about this point of contact. So this we call the instantaneous axis of rotation. So we can understand that if an object is doing pure rolling, then it is doing pure rotation about the point of contact. Okay, I'm going to say that again. When an object is in pure rolling motion, because the point of contact is stationary, we can say that it is doing pure rotation about the point of contact. Is that right? Okay, so what happens in pure rotation? Let's say we have this pendulum. What happens in pure rotation? So this pure rotation happens about an axis which is stationary. Okay, pure rotation. So let's say this is a pendulum. This is oscillating. Okay, so this is rotational motion, and this is rotational motion about this axis. This is pure rotational motion. What is pure rotational motion? Pure rotational motion means that the axis of rotation is stationary. This is meant by pure rotation. Is that right? Okay, so here what we can think is that because this point of contact is stationary and this object is rolling, so just think of a fraction of second. What is going to happen for a fraction of second? If this was the line like this, the line is going to become like this. This is going to be stationary. Okay, so what is happening? We can assume that it is doing pure rotation. Mind my words, it is doing pure rotation about the instantaneous axis of rotation. Is that correct? Do you get that? Do you get that? Okay, so I hope that is clear. So what we can do is, now when we have to calculate the kinetic energy, we don't have to use rotation plus translation. We simply can use rotation. So I am going to say that the kinetic energy for pure rotation is I axis into omega square. So kinetic energy is half I omega square. But what is that I? That I is I axis. Do you get that? That I is the moment of inertia about the axis of rotation. So this is pure rotation. For pure rotation, we can say that. Is that correct? Okay, so now from here we can directly calculate the kinetic energy. So this becomes half multiplied by, I have to find out the moment of inertia about the point of contact. So about the center, it is 2 by 3 mr square. So we can use the parallel axis theorem and find out what is the moment of inertia about the point of contact. It is going to be 2 by 3 mr square. The moment of inertia about the center of mass plus md square. What is the distance between the axis? It is r. So this is r. So this becomes mr square. Okay, and then multiplied by omega square. Now omega square we can write it as v square upon r square. So this becomes half into, and this becomes 5 upon 3, and then we have v square upon r square, and then we have mr square. Okay, so r square and r square gone. So what are we finally left with? We are left with 5 by 6 mv square. Okay, check. We are left with 5 by 6 mv square. Now go back and check what is the kinetic energy we had found out. What is the kinetic energy we had found out using rotation plus translation method? Okay, so we'll get the same result. Is that right? Is the concept clear? So sometimes, yes, if you use instantaneous axis of rotation, your calculation can become easier, but it's not a guarantee. Okay, it's not a guarantee. So in cases when there is pure rolling, sure, it is going to help you. And a lot of cases like that you're going to get. You're going to get a lot of cases where there is pure rolling. So if there's pure rolling, you can think of it as pure rotation about the point of contact and calculate the kinetic energy from there, or even calculate angular momentum directly from there. Okay? I hope that is clear. And then we have got option A as the answer as well. So now let's move to the next question. Alright, let's go for the next question. And here is the next question for you. Another very interesting question. A cubical block of side 30 centimeter is moving with velocity 2 meters per second on a smooth horizontal surface. The surface has a bump at point O as shown. The angular velocity in radian per second of the block immediately after it hits the bump is. Okay, is the question clear? So we have a cube which is on a frictionless surface, it is moving happily, but then it encounters a bump. And when it encounters a bump, you know what is going to happen. Okay, so this object, it is moving like this, but it encounters a bump. So what is going to happen? Can you see that? This object moving encounters a bump. What happens? Right? It will start rotating, correct? It will topple, it will start rotating. So we have to find out what is the angular velocity just after the impact. Alright, so is the question clear? And if the question is clear, then I want to know from you what is the method we need to use to solve this question. So Sujal is saying, nice explanation. Thank you so much, Sujal. I'm glad you are able to follow all these sessions. That's great to know. Alright guys, back to this question. Is the question clear? It's very intuitive, right? It's very easy to visualize. Okay, object, obstacle, it's going to rotate. So we have to find out what is going to be the angular velocity of this object just after the impact. So the question is, what is the concept that we should use? Conservation of angular momentum. Bang on. Perfect. Great answer, Captain Jack Sparrow. Wonderful answer. We can conserve angular momentum, but there's a follow-up question as always. I'm not going to let you go like that. A great answer, but there's a follow-up question about which point. Is it going to be conserved about all points, or there's a special point? And if there is a special point, then which point is that? Aniket is saying angular momentum conservation as net external torque is 0. About which point, Aniket? About which point? Is the external torque 0 about all points? Or there is some special point? Is it the center of mass? Is it some other point? Point of contact. Absolutely. Bang on. Perfect. Great answer, guys. Great answer. Very nice. Very, very nice. Okay, so this object is moving happily, encounters a bump, and now it is going to rotate. Okay, so what we have to think is, just after the impact, okay, just after the impact, the position is not going to change much. Okay, just after the impact, the position is not going to change much. So let's see if we can do it about the center of mass. Okay, let's see if we can do it about the center of mass. So about the center of mass, there's going to be mg and there's going to be normal force. Right, about the center of mass, there's going to be mg and normal force. Okay, so if we calculate the torque about the center, then the torque of normal force and torque of mg is going to be 0. But there is going to be this force, and we don't know the direction of this force. It could be like this, it could be like this, it could be like this. We don't really know what will be the direction of this force. But for sure, the torque above, due to this force, due to this contact force, okay, the torque due to this contact force about the center of mass is not going to be 0. Do you agree? Is that correct? Okay. Which means, if we take this point, if we consider this point, then what is going to happen? There's going to be mg, and then there is going to be normal force, Okay, there's going to be mg and there's going to be normal force. Now mg is going to balance n, okay, because the impact is horizontal. So the contact force that is going to be applied, the contact force that will be there is going to be horizontal because the impact is horizontal. Is that correct? Okay. So in this case, mg is still going to be equal to n, and I'm not talking about a substantial time after. Just after the impact, the position is not going to change much. Okay, so mg is going to be equal to n. So the torque of mg and the torque of n is going to cancel each other. Is that correct? And the torque of this force, is going to be 0 because the force is going to pass through this point itself. So the net torque about this point O is going to be 0. Is that clear? Is that absolutely clear? And is that also clear that we cannot conserve angular momentum about the center of mass? We cannot do that. But we can conserve the angular momentum about this point of contact O. Is that correct? Is the concept absolutely clear? Perfect. So now we have established that we can conserve the angular momentum about the point of contact. So now let's do that. Okay. So what is happening? This is our point over here. This object. Now this object is not rotating, right? It is translating. So we can consider it as a point object concentrated at its center of mass. Okay. Only when the object has rotational plus translation motion, then we'll have to consider. We cannot consider it as a point object. But it is in pure translational motion, so we can consider that there is a point, this entire mass is situated at its center of mass. Okay. So this is the direction of velocity, and we have to calculate the angular momentum about this point. Okay, so we are going to drop a perpendicular, and this perpendicular distance we can see is going to be a by 2, correct? So what is going to be the angular momentum? The angular momentum is going to be mv a by 2. Do you agree? The angular momentum before the impact, just before the impact, is going to be mv r. What is r over here? A by 2. R is the perpendicular distance, right? So this becomes mv a by 2. Now when it hits this point, it will have an angular velocity of omega, and see that this edge, okay, this edge which is in contact with O, will that move or not? When this object topples, when this object begins to rotate, this point which is in contact with point O, is that going to be stationary or not? Think about it. Okay, concentrate at the bottom of the pen. Now when this object comes and hits this point, now when it rotates, do you see that the point of contact is going to remain stationary? Can you see that? Okay, it hits it and now it is going to rotate. So can you see that the point of contact is stationary? Now the point of contact is stationary and it is rotating, which means this is pure rotation. So we don't have to worry about rotation plus translation. Okay, so it is going to be stationary. The point of contact is stationary, which means there is going to be pure rotation. And if there is pure rotation, then the angular momentum is I into omega. Do you agree? When there is pure rotation, then the angular momentum is I into omega. But which I? I about the axis of rotation. Don't make a mistake over here. Just to give you an idea. Let's say this is a rod. This is a rod, and this rod is rotating with an angular velocity omega. Okay, and it is pivoted at the top point. So if I want to find what is the angular momentum, then I'll have to use I of axis. It is in pure rotation about the axis of rotation. Okay, it is in pure rotation about the axis of rotation. So I'll have to take the moment of inertia of the rod about its axis. So this is how I'll find the the angular momentum. So when we are writing angular momentum is equal to I omega, what is that I? I is the moment of inertia about the axis of rotation. Only then we can say this is pure rotation. Is that correct? Okay, so what I have to do is I have to find the moment of inertia of the cube about point O. I have to find the moment of inertia of the cube about point O. Now you guys are going to help me how to do that. Okay, I'm not going to tell you. You guys are going to help me how to find the moment of inertia of the cube about point O. I'm going to wait for your answer over here. How do we find the moment of inertia of the cube about point O? About the center, it's very simple. Do you know what is the moment of inertia about the center of mass for the cube? What is the moment of inertia? The moment of inertia is ma square upon 6. Okay, so the moment of inertia about the center of mass for this cube is going to be ma square by 6, but we'll have to use parallel axis theorem. This axis about O is not passing through the center of mass. Aniket, that's the yes, that is the moment of inertia about the center of mass. You're absolutely right, but that's not the objective. The objective is to find out the moment of inertia about point O. So obviously, yes, we'll have to use parallel axis theorem. So what is I axis? This is going to be ma square by 6 plus m. Now this total length, this total diagonal is going to be how much? This total diagonal is going to be root 2a. So half of the diagonal is going to be a upon root 2. So what is the distance between the axis? The distance is a by root 2. So this becomes a by root 2 ka square. So this becomes ma square upon 6 plus ma square upon 2. And what is that? That is going to give me 4 ma square upon 6, which is 2 by 3 ma square. Alright, so the moment of inertia of the cube about point O is, about the axis passing through O, is 2 by 3 ma square. Is that correct? Now it becomes very simple. Now we can solve it very easily. The initial angular momentum is mva by 2. The final angular momentum is going to be I into omega, and I we have calculated as, was it 2 by 3? Let me check. Come on. Yes, that was 2 by 3. Okay, so for I am going to substitute 2 by 3 ma square multiplied by omega. Is that right? Okay, so m gone, 1a and 1a is gone. So omega is going to come out to be 3v upon 4a. Okay, now let's substitute 3. What is the value of velocity? The value of velocity is 2 into 4 and a is 30 centimeter. So for this we'll have to convert it to meter. So this is going to be 0.3 meter. So this is going to give us 10. This is going to give us 2. This is going to give us 5. So this is going to be 5 radian per second. So the correct answer for this question is going to be 5 radian per second. Is that right? Alright. So we have conserved the angular momentum and we have got this answer. Okay, so what are the key concepts in this question? Number one, when can you conserve angular momentum? Okay, that is the key principle. After that, when we are conserving angular momentum, the angular momentum of an object which is in pure rotation is angular momentum when the object is in pure rotation is I axis into omega. And what is axis? It is the moment of inertia about the axis of rotation. Is that clear? Alright guys, so the correct option for this question is going to be option B, 5, and we're going to have to stop now because time has run out, but we solved very good questions on rotation, some very fundamental basic questions which involve very fundamental and important concepts. Okay, so I hope you find this session helpful. Go back, revise, and if you have any questions, you can ask that away in the next session. Okay, so till we meet again the next time with another very interesting topic, another very interesting question. Till then, keep practicing, keep getting better, and most importantly, have fun with learning. See you very soon in the next session. Thanks for watching, guys.